Hello friends, in the last lecture we have discussed uh, Lagrange's linear equation, method of solution and one example which is based on it. Now in today's lecture we will discuss the rest of the examples which are based on that method. So or on that form. See the another problem given, solve yz into p plus 2x into q equal to xy. So if you observe this given equation, this is in Lagrange's linear form, that is Pp plus Qq equal to R. So first we will consider Lagrange's auxiliary equations. And these equations if we get here, dx upon p equal to dy upon q equal to dz upon R. So p is yz, q is 2x, and R is nothing but right hand side of the equation, that is xy. Now friends, if you have taken here first and third ratio, then what happens you see, by taking first and third ratio, y gets cancelled, x dx equal to there you will get z dz, or there you will get dx upon yz equal to dz upon xy. Here y gets cancelled and take cross multiplication, it gives x dx equal to z dz. And taking that z dz on left hand side, it takes the form x dx minus z dz equal to 0. This equation is in variable separable form. So direct you take the integration, it gives the required one solution. So integrating 2 it gives, or better way you multiply throughout by here 2 first. So if you multiply by 2, there you will get 2x dx minus 2z dz equal to 0. And then you take the integration. There you will get 2 into x square by 2 minus 2 into z square by 2 equal to, it gives c1. 2 on LHS from first and second term gets cancelled, and it gives one solution u equal to c1 as x square minus z square equal to c1. Now taking second and third fraction, means if you have taken this second and third, shift y here, xx gets cancelled. So there you will get 2y upon 2x equal to dz upon xy. So here, friends, xx gets cancelled. Shift this 2 here and y here. So it gives y dy minus 2 dz equal to 0. Integrating it gives, or you again multiply here by 2. So if you multiply by 2, there you will get 2y dy minus 4 dz equal to 0. And then take the integration, so it gives another solution phi equal to c2 as 2 into y square by 2, integral of first term, 2 gets cancelled, there remains y square, minus 4 as it is, integral of dz is z, equal to, you will get constant of integration, that is c2. So friends, here we obtain this as e equal to c1 and this as v equal to c2. These two solutions, if you have taken together, then these two solutions give the solution of these simultaneous linear equations. But if you have considered here these obtained solutions in the form phi of u comma v equal to 0. U is what? X square minus z square. Phi is what? Y square minus 4z. It gives the general solution of what we call it as a Lagrange's equation, yz into p plus 2x into q equal to xy. In my sense, if you understand here what I explained or how to find the solution. Now I will proceed towards the another example. Solve xz into bracket z square plus xy into p minus yz into bracket z square plus xy into q is equal to x raised to 4. So again this equation is in the form pp plus qq equal to capital R. So the Lagrange's auxiliary equations for this given equation takes the form dx upon p equal to dy upon q equal to dz upon r. So p is what? Xz into z square plus xy. Q is what? There you will get minus 2yz into z square plus xy. So I forgot to write here two friends, is equal to dz upon r means x raised to 4. Now, if you have taken here the first two fractions, then that 2 is not there. Wrongly, I have written here 2 and here 2. That 2 is not there, friends. So you take the precaution. So here z square plus xy, here z square plus xy gets cancelled. Here dy upon yz and dx upon xz. So zz gets cancelled and it gives dx upon x, shift this term on LHS, dy upon y equal to 0. So friends, this 2 is not there because it is not given in the question. So this 2 is not there. This is also not there. So after simplifying, it gives equation like this one. And this equation is in variable separable type. So taking the integration, it gives log x plus log y equal to log c1 as one solution, or it gives log xy equal to log c1. So it gives xy equal to c1, means u equal to c1 as one solution. Now taking first and third fraction. So if I taken first and third fraction, uh, actually here wrongly I have written here dy, but you remember taking first and third fraction, what you have to do, you see there you will get what, dx upon xz into z square plus xy is equal to dz upon x raised to 4. And then friends, if you observe here, one x gets cancelled, or shift this x raised to 4 here and this term here. So it gives what? X cube dx is equal to z into z square plus xy. But xy is nothing but what? C1, and that is substitute here. So here coefficient of dx is function of x only. Coefficient of dz is function of z only. So this equation is again in variable separable form. So what you have to do, you take the integration, it gives another solution. So integral of x cube, it gives x raised to 4 upon 4 minus, there you will get integral of z cube, you will get z raised to 4 upon 4. Then there you will get, actually you will get integral of z c1, c1 is constant. Integral of z dz, it gives z square upon 2. And if we multiply throughout by 4, there you will get minus 2c1 is equal to, it gives it to be 4c2, or 4c2, and you take it as a c2 only. That is the constant of integration. And resubstitute here value of c1. C1 is what? Xy. So we obtain one solution as xy equal to c1. This is u equal to c1. This is another solution, phi equal to c2. So the from equations 3 and 5, it gives required general integral or general solution of this equation as phi of u comma v equal to 0, that is xy comma x raised to 4 minus z raised to 4 minus 2xyz square equal to, it gives it to be 0. Here phi is what? Phi is an arbitrary function. Now I will proceed towards the next example, that is solve py plus qx equal to xyz square into x square minus y square. So this equation is again in the form pp plus qq equal to r. So the Lagrange's auxiliary equation here in this case takes the form dx upon p equal to dy upon q equal to dz upon r. So p is what? Y. Q is what? X. And r is what? X, y, z square into x square minus y square. So if you have taken first and second fraction, it gives x dx equal to y dy, means x dx minus y dy equal to 0. So direct you will get this equation in variable separable form. Take the integration, it gives one solution as again you multiply here by 2. So 2x dx minus 2y dy equal to 0. And then you take the integration. There you will get integration 2 into x square upon 2 minus 2 into y square upon 2 equal to c1. So 2 from each term on LHS gets cancelled, and it gives one solution as x square minus y square equal to c1, that is u equal to c1. Now taking here second and third fraction, means this and this fraction together, what happens, you see there you will get dy upon x equal to dz upon x y z square into x square minus y square. Further friends, what happens, this x gets cancelled, and it gives what? Shift this y here, y dy is equal to dz upon z square into bracket x square minus y square. But x square minus y square is what? C1, means it gives y dy equal to dz upon z square into C1. And then friends, this equation is also in variable separable form. So direct you take integration. So integral of y dy, it gives what? That y square upon 2. Then integral of this 1 upon c1 you will get outside constant, And integral of dz upon z raised to 2, we can write it as integral of z raised to minus 2 dz, and it takes the form z raised to minus 1 upon minus 1. And then resubstitute value, simplify, it gives here the required solution to be like this one. And further, if we multiply by z, then it gives what? If you multiply by z and if you substitute the value of c1 as x square minus y square, it gives the required solution to be what? Or here, no need to multiply by z, only put here value of c1 as x square minus y square. It gives another solution, y square as it is, value of c1 is what? X square minus y square plus 2 upon z equal to, it gives c2. So once you know one solution as E equal to C1, another solution as V equal to C2, these two solutions, if you are taken together, then these two solutions give the solution of these simultaneous linear equations. But if you have considered here these two solutions in the form of phi of u comma v equal to 0 or u equal to phi of v, then in that case, uh, that becomes general integral of this Lagrange's equation, that is of the type pp plus qq equal to r. So required general integral, you will get this phi equal to, this is v equal to phi of u, v equal to phi of u, where phi being an arbitrary function. Now we will proceed towards here one more example, friends. Solve y minus zx into p plus x plus yz into q equal to x square plus y square. So again this equation is in what form? pp plus qq equal to r. So Lagrange's auxiliary equation takes the form dx upon p equal to dy upon q equal to dz upon r. Now here in this case, if you have taken any two ratios together, it can't give the required solution. So you apply here method number 2, that already I have explained under the topic, which one? That simultaneous linear equations. So you select here set of multipliers, uh, two set of different sets of multipliers to get the two independent solutions, E equal to C1 and P equal to C2. So if you choose here the set of multipliers in such a way that value of numerator becomes exact differential, and at the same time denominator must be equal to 0. So if you use here one set of multipliers as y, x and minus 1, then from this equation 1, we can write each fraction as y dx plus x dy minus dz upon multiply this by y, this by x, and this by minus 1, and take the addition. So here you will get y square, this minus y square gets cancelled, then here you will get x square, this minus x square gets cancelled, and here you will get xyz minus xyz, this plus xyz gets cancelled, means we get here denominator as 0, and see this numerator is an exact differential. Why? Because we can write this numerator as derivative of some function. So we can write y dx plus x dy minus dz equal to 0. This first two terms is nothing but the total derivative of xy, that is d of xy minus dz equal to 0. And integrating it gives integral of first term, you will get xy minus integral of dz, you will get z equal to c1, means it gives one solution as e equal to c1, means xy minus z equal to c1. Now choose the another set of multipliers x minus y and z to get the another independent solution. So if you have used here the set of multipliers as x minus y and z, then each fraction in equation 1, that is in this equation, becomes what? X dx minus y dy plus z dz divided by, you will get here this denominator to be 0, you have to check it. So multiply this by x, this by y, minus y, and this by z, and take the addition. There you will get this denominator plus xy, this minus xy gets cancelled. Here minus x square z, this plus x square z gets cancelled, and here minus y square z, and this plus y square z gets cancelled, means you will get numerator as exact differential x dx minus y dy plus z dz upon 0. So it gives here what? 0 into each fraction, you will get 0, means you will get this numerator equal to 0, means x dx minus y dy plus z dz equal to 0. Now, this is an exact differential because coefficient of dx is x, coefficient of dy is y, coefficient of dz is z, means these are functions of x, y, z respectively. So integrating it gives another solution as a x square minus y square plus z square equal to c2. And friends, once you know here these two solutions, C equal to C1 and V equal to C2, then in that case, the general solution of the equation is given as phi of u comma v equal to 0, that is phi of xy minus z comma x square minus y square plus z square equal to 0. So in my sense here, friends, you have understand here the solution of each and every problem taken from today's lecture. Afterwards, here three or four examples are left to discuss. Example number 6, 7, and in my sense here only two examples are left to cover from this part. So I will cover here these two examples in the next lecture so that we will finish uh, your syllabus, means here the article Lagrange's form from your syllabus. So today we stop here. Have a good day, friends.